4 is describing the relationship between two variables. And so up until now, chapter 3 that we just got done with, it was just one variable. Weights, GPAs, whatever we had, we put it in list 1 and we computed the stuff. Now we're going to have two variables, kind of like an X and a Y, an independent and a dependent. So it's very algebra based. So if you guys have taken like an elementary algebra, this kind of follows that a little bit, all right? So it says data for a single variable is actually called univariate. Uni meaning one, variate meaning variables. Univariate. So that's what we just got done doing in chapters 2 and 3. We were given data sets of one variable, favorite colors, if it was qualitative, heights or weights, if it was quantitative, and we organized it in some numerical or graphical way. Most of the real world problems, though, have more than one variable. Multivariate is what that's called. Multi meaning many, variate meaning variable. But fortunately for us, that's way too complicated to compute, so we don't have to worry about it in this class. So we're just going to focus on two variables. Any guesses on what that's called? What's the prefix for two? Bi. So it's going to be bivariate data. So like I said, it'll be kind of this independent, dependent kind of concept. Does this affect this? All right. So on section 4.1, we're going to introduce scatter diagrams and correlation. When we have two variables, they could be related in one of several different ways. One, they could be totally unrelated at all, so one does not explain the other. Or two, which we're more interested in, the explanatory variable could be used to explain the other, or the response variable. Guys, this is kind of like our x, the independent variable. And remember, back in algebra, y equals mx plus b? Depending what your x was, it affected what your y was, right? So your response or dependent variable is your y, dependent. Bless you.
Thank you.
All right. So they're using two words, and I think it was even, wasn't it you, Spencer, that mentioned that? Like, why don't we just use x and y? And that's exactly what they do in this section. Explanatory is like your x, your independent variable. The response is like your y. Those are those vocab words that we learned in chapter 1. So let's just make sure we can identify which one's which. And this is basically review, guys. We had to do this in chapter 1. So say we're talking about rainfall and plant growth. Those are two different variables. How much rain you get and how much your plant is growing. But they could have a relationship. So one could be explaining the other. So which one do you think is explaining the other? The rainfall, right? The rainfall amount are going to explain how the plant's growing. So that's the response variable, the plant growth. Is that okay? Lurking variables, does anybody remember what lurking variables are? It's my favorite vocab word.
It's the ones that, like, you don't think about them initially, but they're there.
Exactly. They're there, they affect what you're studying, but you're not thinking about them initially. So basically, we know real life is multivariate. So all those other variables we're not considering are the multivariate part. So the lurking variables, for example, what are other variables that could explain how plants grow? And we've used this example before. So what was it? Soil, sun, oxygen, and we could keep going, right? So please realize there's, in this situation, plant growing, there's many variables. It's really a multivariate thing. But in chapter 4, guys, we're just going to focus on two, the rainfall and how it affects that plant growth. All right, exercise and cholesterol levels, you kind of can argue both ways, but in general, which one explains the other? Exercise usually explains your cholesterol. So exercise is your explanatory, and what is it affecting? Your cholesterol. Can you see how it might be flip-flopped in some cases? Maybe you go to the doctor and they're like, hey, your cholesterol levels are a little high, you need to start exercising, right? So, and actually, that's my instance. I have one of my bad, there's HDL and LDL, right? Which one's the bad one? Does anybody know? Is it LDL? Do we know? You guys are nursing students, but you haven't quite gotten there, right? I actually have, my bad one's high, and I don't exercise. So my doctor's like, well, maybe you should think about exercising. So mine's a little bit flip-flopped here. All right, what's something else? What are some other possible lurking variables that might affect somebody's cholesterol levels other than how much they exercise? Their diet. What else? There's only really one other thing I can think of. Genetics, yep, that's what I would think of. Sometimes, unfortunately, we just get bad genes, so you could be one of the healthiest people as far as eating and exercising, but your cholesterol level, that's what I say. I just have bad genes. No, I really don't have bad genes. I need exercise. All right, so this is not really anything new, okay? It's just now that we're gonna put them together, we're gonna start graphing them, we're gonna see what type or how strong a relationship they have. And it all starts with a scatter diagram. And so that's your first fill in the blank here. A scatter diagram is honestly exactly what its title is. It's a diagram that has scattered points, all right? So if you read the definition, it says it's a graph that shows the relationship between a quantitative variable measured on the same individual. Each individual in the data set is represented by a point on that scatter diagram, all right? The explanatory variable, which is your independent variable x, is planted on the horizontal axis, and then your response variable y, what is affected by that, is planted on your vertical axis, and then we have the points. Please note it says you don't connect the dots. It's literally a scatter diagram, all right? So I know we have a couple golfers in here. Who said they golfed? I remember reading it on. Okay, I golf, air quotes. I really don't, but I go with my husband sometimes. But what this is your independent variable here, guys, is how quickly you swing your golf club, okay? And the question arises, how quickly you swing your golf club, does that affect the distance that your golf ball travels? And in general, we would probably say yes, right? And so what they did was, I grabbed this from the book, is this is the same golfer, same golf club, you know, same day. He swung 1, 2, 3, 4, 5, 6, 7, 8 times. He swung 8 times, okay? And they measured the speed at which he swung his golf club and then the distance that the ball goes, okay? And that's what a scatter diagram is. It just plots a point, x, comma, y. How many of you guys have had an algebra class where you've plotted points? That's what scatter diagrams are, okay? The whole idea is, do you see kind of a trend forming? Is it a perfect line? No, but do you kind of see a line forming that the further you, or the faster you swing your golf club, the further that ball is going to travel, okay? So we're going to talk about that relationship. What type of relationship exists that when the points follow a general pattern of a line, it's called a linear relationship. So it's not going to be perfect, guys. This is real life data. It's not going to be this perfect line, but in general, if you kind of see a line forming, it's called a linear relationship. If you still have a pattern, so it follows a general pattern, but the pattern is not that of a line, it's called a nonlinear relationship. And sometimes, guys, you might plot your x and your y, and there's no pattern whatsoever. You're just going to have no correlation or no relationship. Okay? So sometimes they just have nothing to do with each other. All right? So let's focus on the linear ones first. If you plot it, just like the golf club example, and when the speed went quicker, the golf club went further, what is this called? This is called a positive relationship. Remember back in the day when you talked about lines, you talked about the slope? Okay, this would have a positive slope, and so that's a positive relationship. So any guesses on what this one is? As the x increases, the y decreases? You got it. No tricking you guys. So this might be the more time you spent partying the night before a test, this is your test score, right? So the more hours spent out and not studying, your test score is going down. So they're related, yes, but in a negative way. All right. So I'm going to give you some examples. So what are some examples of positive relationships? The first one, I know there's a lot of words here. All it's saying is that above average values of the x go with above average values of the y. So like when you move left to right, where high is high, but also low is low, okay? So we have a variety of things, but one I have is age and height for children. And I'm putting them in quotes so you know what the variables are, okay? So the age is your x variable, and the height would be your y variable. So do you guys agree that this is a positive relationship? Meaning as the x increases, as your age increases, your height is increasing as well for kids. You guys agree? As kids, most kids, as they grow older, they grow taller. Okay. Let's also put down temperature and sales of ice cream. So ice cream sales. Again, temperature is that independent, that x variable, and ice cream sales are that dependent, that y variable. Do you agree that it's a positive relationship? As it gets hotter outside, ice cream sales are increasing. Yes. Anybody like me where it doesn't matter if it's 32 degrees outside and you're still eating ice cream? Yeah, thank you. Mm-hmm. So the temperature doesn't affect our sales, but in general, like I'm from Troy, so like Bobby's is in Maryville. They're only open, in the hotter months. They're closed during the winter. So in both of these, realize as one increases, so does the other. All right, we're just going to flip it now with a negative relationship. The negative relationship shows you that highs and lows are paired together, meaning when your x value is high, it's with a low y value, and when your x value is low, it's with a high y value. So they're just exactly opposite. What are some examples I have? Let's do age again. Age and 50-meter dash time for children. Age and 50-meter dash time for children. So how old the child is would be our x-axis. So as the child gets older, what would we expect their dash time to do? It should decrease, right? They should get faster. So maybe a mile run. Did you guys ever have to do PE, those like physical fitness tests? Oh my God, they were awful. But you know how they had those standards you had to meet? As you got older, your mile time got lower, right? You became faster, and that's all this is saying. As you get older as a kid, and notice I say for children because when you get to a certain point, you start getting slower. So as you get older as a kid, your 50-meter dash time should quicken, or AKA go down. Another one I have is temperature. Temperature and hot chocolate sales. Temperature and hot chocolate sales. So I'm trying to kind of just mimic the ones above. Above, as it got hotter out, our ice cream sales were going high. Well, don't you think that's the exact opposite for hot chocolate, right? As it gets hotter out, what's happening to the hot chocolate sales? They're going down. I didn't use coffee because if anyone's like my dad, he lives in Vegas, and he'll be sitting out on his porch at 118 degrees drinking a hot cup of coffee. So I feel like coffee's not the best example there because a lot of us just drink it no matter what. But in general, hot chocolate, you're drinking it when it's cooler, right? So if temperature is getting hotter, you're usually not buying it. All right, so those are the linear things. Honestly, guys, when it comes down to it, Chapter 4 is going to be focusing on the linear stuff. We still have to introduce and kind of talk about the nonlinear stuff, but you're not going to do a whole lot with it. And that's all it's doing down here. These two examples are of a relationship that exists. Do you guys agree that in general there's a pattern there? But it's just not a line, so it's not a linear pattern. This is more kind of like a parabola, an arch. This is more like a cubic, okay? So if you see a pattern, it's still a relationship. It's just called a nonlinear relationship. All right, go ahead and flip it over to the top of page 3. And this is what it looks like when there's not really a relationship at all. I just kind of just say, like, if you're a painter and you just took paint and you just went like this on a canvas, It's just everywhere, right? No matter what happens as you move to the right, you have some high, you have some low, it doesn't matter. There's no pattern going on. So like anything that's just kind of scattered or like a horizontal line is no relationship at all. So that would be called no relationship or no correlation. All right, so let's focus on these. What are some like real life examples? Like where in life might we see a parabola-shaped relationship? Well, one would be age and height for people. Notice I took off the children and I put people in general. How is that a nonlinear relationship? Well, would you agree, in general, as you age, you get taller, but then at a certain point you kind of max out, and then what happens? You start shrinking, okay? So is this quite a parabola? No, we're not Benjamin Button where we're going all the way down to like baby height, right? But it's in general kind of this arch and then like a little hook almost, right? It's almost like a candy cane. So the shape of this would be like, okay, I'm growing, and then I'm gonna max height, and then I start to shrink a little bit. There's an obvious pattern there, it's just not a linear pattern. Another one would be temperature, and comfort level for people. So comfort level, meaning if you had to rate how comfortable you were in this classroom from 1 to 10, is it affected by how hot or how cold it is in here? Yeah. Do you guys agree that if it was really, really cold, you'd be miserable, so you'd rate it a lower comfort level? Yeah. Would you agree if it was really, really hot, like 100 degrees, you would rate it a low comfort level? Yes, but would you agree if it's in that middle, little perfect 68 to 72, you'd rate it high? So that's a perfect example of that parabola, that arch. As it's cold, you have low levels. As it's hot, you have low levels, but you kind of have that happy medium point in the middle where you would have the highest levels of comfort. So he basically mimics a perfect parabola. This is probably like 70 degrees. I'll put 100 here. I'll put 40 there, right? So our x-axis is the temperature, right? And our height, if I drew the height, the y-axis, that's your comfort level. So we're going to rate it pretty low when it's cold and hot, but we're going to rate our comfort level pretty high when it's that nice comfort zone. All right, when it comes to no relationship, guys, you honestly could pick any two quantitative variables that have nothing to do with each other and match them up, okay? So what about temperature and shoe size? Does the fact that it says it's 90 outside affect your shoe size? Maybe. Some people might argue that their feet swell. But in general, how hot it is not saying I'm a size 10 compared to a size 6. All right? How about your age and phone number? Or last digit of your phone number, because we probably only want one value there. How old you are, does that have anything to do with what type of phone number you have? No. Okay, we'll write last digit. So if you had to plot this, you know, from, when did you guys get phones? How young were you? Anybody think they were really young when they got a phone? I was 16. Anybody get it before 16?
I got mine when I was 6, but that was because I walked back and forth to school.
Okay. So say we started plotting age 6 to however, like my 94-year-old grandma had a cell phone, right? So we plot the ages on the x-axis, but then we plot the last digits of the phone numbers. What's going to happen? You know what I mean? As we move in our age, the last digit of our phone numbers all vary. So there's absolutely no pattern there whatsoever. Okay? Are there any questions with scatter diagrams and the patterns that we're studying? Positive, as one goes up, so does the other. Negative, as one goes up, the other goes down. And that's really what we want to focus on. All right, so this is where you start throwing up a little bit in your mouth, right? So the whole question is, if you see a linear pattern there, if you see that it's somewhat related to each other, the question is, how related is it? How strong is it? So Pearson was a mathematician who came up with this correlation. So let's go ahead and read it. It's called the linear correlation coefficient, and that's really what I'll call it. But it's also called the Pearson product moment correlation coefficient. Try to say that 5 times fast. What the heck is it, guys? It's a measure of the strength of the linear relationship. Okay? How strong is that linear relationship? How much does rainfall really affect how a plant grows? Or how much does your exercise really affect your cholesterol level? So, if we were doing it for a population, which is basically impossible, the Greek letter rho, it's like a crazy P, is what we would use, but we're not doing anything with the population. What we're doing is we're doing the sample correlation coefficient, and that is R. Okay? The sample correlation coefficient, so it's just another guy to add to your little dictionary of symbols, basically, okay? So anytime it asks for linear correlation coefficient, you want to remember that it goes with R. All right, how would we find him? Do you guys remember what this big guy was? It was the sum of all. What are we summing? The stuff that's right behind it. Since these are right next to each other, guys, this is technically multiplication, okay? And I know you're not 100% familiar with it, but what they are, they're actually the z-scores, okay? This is the z-score for the x variable. And this is the z-score for the y variable. So remember how you found them was you took your individual data value minus the mean and divided by the standard deviation. We would do that for every single data value for x. So go back to the golfer, okay? X was his club speed. We take every single one of his club speeds individually, subtract the mean, and divide by the standard deviation. At the same time we're doing that, we would do the same thing with his y value, which was the drive, how far the ball went. So you'd pair them up, multiply, pair them up, multiply, and then you'd add all those at the end and divide by n minus 1. Software. We're using a calculator, okay? Please do not go here and try to use this formula. Chapter 4 is going to be all done on a calculator, which is really nice. What you want to take from this then, again, is on your calculator, a bunch of stuff's going to be thrown at you. You want to know that R is that correlation coefficient. Okay, let's talk about it before we actually find it, okay? So R, guys, is kind of like the slope. It's going to tell you how strong it is based on what number it's close to and what sign it is, okay? So R is only going to range between -1 and +1 inclusive. Inclusive means what? Including, right? So it can be -1 and it can be +1. That just means it's a perfect relationship. And since it's real life data, guys, you rarely are going to get that, okay? Every line you ever did y equals mx plus b in your algebra class, its coefficient would be r or -1 because it was a perfect straight line. It wasn't real life data, okay? But real life data is most likely going to be some decimal in between, all right? And you probably can fill out the rest of this without me. If we are with a perfect positive relationship, what do you think our r is going to be? +1, you got it. A perfect positive relationship means those dots line up perfectly. We can draw a straight line. We can come up with the equation y equals mx plus b. Nothing falls off of that line. Similarly, a number 3, if it's a perfect negative relationship, guess what our r is? -1. But this is not practical. This is not real life. This is not what you're probably going to see in this class, okay? So you're going to see values close to 1 and close to -1, right? So the closer you are to +1, the stronger positive relationship you have, okay? And similarly, the closer you are to -1, the stronger your negative relationship's going to be. You kind of get it from everything we've said already, but number 6 just says positive values of R correspond to a positive relationship. So if you see like a negative line, you know right off the bat R should be negative something, okay? And so kind of keep that in mind because they're going to have matching games for you guys. They're going to give you data, and they'll give you like scatter diagrams, and you have to match the scatter diagram with the correct R. Never match a decreasing line with a positive R and vice versa. We know the signs, okay? This is what we want to take from 6, though. The closer you are to 0, like it's a bad relationship, okay? No relation. So if you're at like 0.2 or -0.4, kind of think of it as a test score, right? If you got a 40 on a test, you wouldn't be very happy with it, right? So then that's not a very good relationship. But if you got a 70, you know, you're like, that's passing, that's not bad, that would be a stronger relationship. This is something you guys are going to like. But you guys actually probably were the best class I've ever seen taking exam 1 and putting your units down, okay? But R is unitless. It doesn't have a unit, okay? So when we find R, we'll put R equals point blah, blah, blah. No unit behind it, which is nice. You don't have to remember that. And then this last one, it's not resistant. What did it mean to be resistant? Does anybody remember? You're strong, you hold your spot, big and small values don't throw you off by a whole lot. Well, since R depends on your mean, which is not resistant, R is not resistant either. A really, really bad swing of it, like say he was swinging his golf club and somebody, does anybody used to watch like Jackass? Are you guys too young for Jackass? Anybody watch that back in the day? Like, you know, they go to a golf course and then like do the blowhorn like right when they're swinging. Say that happened when he was doing this, you know, that's going to be an outlier. That's going to throw off his swing. And so then that would make the R really bad. And in general, everything else looked good except for that one swing when they blew the horn, okay? I'm going to grab my book real quickly and show you what I'm talking about as far as the matching goes. So your first couple problems on Chapter 4 homework, guys, are going to just be something like this, where the graph is matched with your R, okay? So notice this is a perfect positive relationship, so it's a positive 1. This is a perfect negative relationship, so it's a negative 1. Both of these are positive relationships, right? But do you agree this one's worse than this one? So notice this is 0.9 and that's 0.4, okay? So the crappier it looks, the lower the R is. And then these are just the flip-flop. Again, these are both generally going down in a negative direction, but he looks a lot better. So he's a negative 0.9, close to negative 1. But he doesn't look that great, and he's a negative 0.4. And notice this, guys, I don't even know what's going on there, right? So he's very close to 0. And even though there's a pattern, it's neither positive nor negative, so that's close to 0 as well. It's called a linear correlation coefficient. So we don't even care if it's a pattern. It's not a linear pattern, so we don't care. All right, so how do we find this guy? I used to be mean. I put air quotes mean. It really wasn't that bad. But I used to have you do it with that formula one time just to say, it's really not that bad. You guys have the skill to do it. But I'm like, why even waste time? You have the skill to do it. Believe me, you could do it if you had to do it, just kind of like we did standard deviation by hand one time. But we're going to find the linear correlation. And what I'm going to do is I'm going to go ahead and get your calculator out. But guess what I have for you? Your Chapter 4 calculator cheat sheet. So this will get you through Chapter 4. Chapter 4.1, 4.2, and 4.3 are all on here, okay? So I don't know if you guys have been labeling these, but you can label it chapter, I think maybe 2's there.
There's only like 3 seconds in chapter 4.
Yes, it's very short. And 4.3 goes really quickly. 4.1, guys, and 4.2 are the longer of the two. So just bear with me today and Monday. All right, okay. So I always, when I make these, first of all, try to give you a cheesy title. So whose line is it anyway? Anybody ever watch that? Yeah, okay, good. So I'm like, my jokes are slowly dying because I get older and older and you guys stay the same age. So what this is, it's using your graphing calculator to compute the correlation coefficient R. So that's 4.1. The least squares regression line, that's 4.2. And the coefficient of determination R squared, that's 4.3. So this will get you through all of it. I always give you like a generic example to refer to later. But let's just kind of follow these steps, but with our golf club example, okay? So it says a golf pro wants to investigate the relationship